Hello everyone, welcome back to the channel. In this video, we are going to discuss about important rules which are helpful in filling the electronic configuration of various elements. Now, these rules are very important, so just stick with the video and watch it till the end so that you can understand all the rules properly. One important disclaimer is there that before going through these rules, you should have the proper idea about the quantum numbers, or we can say the important aspects of quantum mechanical model of atom. Understood? Now let's go through it. Now the first point says the first rule is Pauli's exclusion principle. Now this first rule, that is Pauli's exclusion principle, what does it say? Let's understand. Now according to this principle, an orbital can have maximum of 2 electrons and both the electrons must be of opposite spin. What does that mean? Now we know the orbitals are designated like squares, right? This is how we draw the orbitals. This principle says that an orbital can have maximum of 2 electrons only. It can accommodate maximum of 2 electrons and both the electrons should be of opposite spin. That means if one electron is having this spin, other electron must be like this. So this type of configuration is acceptable. But if we draw the electrons like this, if I draw the electrons like this is not acceptable. Or we can say if I draw the 2 electrons in the orbital like this is also not acceptable, right? So both the electrons should be of opposite spin, right? It can have maximum of 2 electrons. Second principle about the Pauli's, second point about Pauli's is that any 2 electrons cannot have same set of all the 4 quantum numbers. Now we know the 4 quantum numbers are N, L, M and S. So this point says that any 2 electrons, they cannot have all the 4 quantum numbers of same value. So we can interpret this statement is that any 2 electrons can have 2 values of quantum number same, 3 quantum numbers value same, but can never be all the quantum numbers values same, right? For example, if you understand this thing, let's say we have 2p subshell. Let's say we have 2p subshell. Now in 2p subshell, let's say we have 2 electrons. These 2 electrons are there. Now this electron is in 2px, let's say this electron is in 2py, right? So for these 2 electrons, we have to check the values of, we have to check the different quantum numbers. So let's try to do this thing. Now for this electron and for this electron, for this electron n value is 2 and for this one also n is 2. For the first electron the value of L is what? Now here p subshell is there and for p subshell the value of L is 1. So here also value of L is 1. Now if you talk about value of M, right? The value of M for 2px is what? The value of M for 2px is minus 1 and for 2py it is 0, right? So because of these 2 electrons which are present in different orbitals, you see the value of n is same, L is same, but the value of M is different. That is magnetic quantum number is different here. So, and also if you talk about spin, if you talk about spin of these electrons, both the electrons are having same spin, plus 1 by 2 and plus 1 by 2. So you see here that N, L and S, they have same values, but the value of M is different for these 2 electrons. So this is how we justify the statement that any 2 electrons cannot have same set of all the 4 quantum numbers. So all the 4 quantum numbers will not be same for any 2 electrons. Similarly, if we talk about, let's say, 2 electrons which are present in the same orbital, these 2, and let's say this is 2s. We know S subshell has only 1 orbital. Now, for these 2 electrons, if we talk about the value of N, the value of N for these 2 electrons is what? It is 2, right? Similarly, value of L for these both electrons is 0. The value of M for both these electrons is 0. But the value of spin, one electron is plus half, or we can say clockwise direction, its movement, its rotation is clockwise direction, and second electron is minus 1 by 2, that is anti-clockwise direction. So you see here also that first three quantum numbers are same for both the electrons, but the last quantum numbers, that is spin quantum number, is different. So that is how we finally justify this statement. Second rule is Aufbau principle. Now this principle is very important for the understanding of electronic configuration in the elements, and this is the crux of this configuration rules. This rule says that all the electrons which are filled in the orbitals, or we can say in the subshells, the electrons which are filled in the subshells, it is done in the increasing order of their energies. Increasing order of the energies of what? Energies of subshells. Now, what is the meaning of the statement? The energy of these subshells is decided using the n plus L rule. So, the important thing here, according to Aufbau principle, is n plus L rule, right? What is n plus L rule? According to this rule, lower the value of n plus L for any subshell, lower will be its energy. So any subshell which has lower energy will be filled first, and the subshells which are having higher energy will be filled later, right? That means in the increasing order of their energy, electrons will be filled in the different subshells. Now we know that in the first shell, we have only one S, that is one S subshell. In second shell, we have two subshells, 2S and 2P. In third shell, we have three subshells, 3S, 3P and 3D. In fourth shell, we have four subshells, 4S, 4P, 4D and 4F. In fifth shell, again we have four subshells, 5S, 5P, 5D and 5F. And similarly in the case of sixth also. Now let's try to find their n plus L value. Now n is basically what? N is the principal quantum number and L is the angular momentum quantum number. And both these values are given with respect to every subshell. In the case of 1s, the value of n is 1 and the value of L is 0. So it is what? 1 plus 0, it is 1. Similarly, in the case of 2s, again here also, we have 2 plus 0, 2. So to solve this, just simply in a way, we can do this thing that just to remember it back, we know the codes of orbitals or different subshells. For S subshell, the value of L is 0. For P, the value of L is 1. For D, the value of L is 2. And for F, the value of L is 3. Right? Now in the case of 2P, it is what? 2 plus 1, 3. In the case of 3S, 3 plus 0, 3. Similarly, in the case of 3P, it is 4. 3D, it is 5. 4S, it is 4. 4P, it is 5. 4D, it is 6. 4F, it is 7. 5S, it is 5. And 5P, it is 6. 5D, it is 7. 5F, it is 8. Now in the case of 6S, it is 6, then 7, then 8, then 9. So this is the order of n plus L values of different subshells. Now let's try to arrange them in the increasing order. The lowest energy will be of 1s. So electrons will be filled for the very first in the 1s subshell. After 1s comes 2 value, that is value 2 n plus L, right? So only 2 has this value, so after 1s comes 2s. Next is 3 value. Now the 3 value belongs to two subshells, 2p and 3s, right? Now here, important thing, that if n plus L value comes same, then what to do? If the value of n plus L comes same, then how do we decide? So remember this thing, if ever the value of n plus L comes out to be same, then the subshell which has lower value of n will be of lower energy. Simple, right? We can easily write that if n plus L value is similar in the case of two orbitals, right? Similar in the case of subshells, then subshell having lower value of n, has less energy. It has less energy, right? Simple point. So that means in the case of 2p and 3s, 2p comes first, then comes 3s. After 3s comes which one? 3p. 3p is 4, and then comes 4s because 4s is also 4. So after 3p comes 4s, right? 4s is also 4. After 4s comes 3d. Now 3d is quantum, 3d is n plus l 5. After 3d comes 4p, and after 4p it is 5s, right? Up to 5s it is 5 value, n plus l. Then comes the value of 6. After 5s we have 4d, right? 4d has the value of 6. After 4d we have 5p. After 5p we have 6s, like this. After 6s we have 6 values done. Then comes 7. So we have 4f. Once we have filled the 4f, then we have 5d, and then we have 6p, and so on. So this is the order in which subshells will be filled, or we can say the electrons will be filled in the subshells by arranging them in the increasing order of their n plus l values. Now one important thing. Okay, we'll do it later, right? So this is how we arrange it. This is the particular order of subshells in the increasing order of energy. Now, one more important thing is there, that how do we remember this order, right? So a very short trick is there, a very interesting way to remember this order is, we know in the first shell we have one subshell, so in the first shell we have only one S. In second we have 2s, 2p. In third we have 3s, 3p, 3d. Similarly, fourth, fifth, sixth, and seventh. In this way, we will write all the subshells of a particular shell, right? Now, mark the arrows in the downward direction like this, from left to right. Sorry, from right to left. From right to left in the downward direction, mark the arrows like this. 1s, and then comes 2s, then comes 2p and 3s, and then comes 3p, 4s, 3d, 4p, 5s, then comes 4d, 5p, 6s, and after that comes 4p, 5d, 6p, 7s, in this order, right? And after that comes 5f, 6d, 7p, like this. So if you see, if you compare this arrangement of arrows with the above mentioned order which we have just done, the first order first comes is 1s, right? So 1s is there, yes. Then 2s and 2p. So that means first comes 1s, then we fill 2s. After 2s, the arrow is coming from 2p to 3s, right? This is the direction of arrow from 2p to 3s. So 1s, then 2s, then 2p to 3s, then 3p to 4s, and then 3d, 4p, 5s. Then we have 4d, 5p, 6s, right? In this direction of arrows, we have to remember the particular order of electronic configuration, right, of filling of subshells. So I hope you understood how do we decide and how we can use the Aufbau principle to fill the electrons in the subshells. Now important thing is when we go through the different configurations, so let's do one thing, let's try to write the configuration of some elements. And before going to that thing, just I want to give you a little bit idea that in the case of S subshell, if we have S subshell, right? S subshell has how many orbitals? It has only one orbital. And since it has one orbital, and one orbital can only occupy 2 electrons, so maximum electrons in S subshell is 2. Similarly, if we talk about P, now P subshell has 3 orbitals. That means the number of electrons will be what? Double. It will be 6. In the case of D, the number of orbitals are 5. So it can have 10 electrons. And similarly, in the case of F subshell, number of orbitals are 7. So it can have maximum of 14 electrons, right? Because we know each orbital contains maximum 2 electrons. So the number of electrons will be double the number of orbitals. Now, let's try to write the electron configuration. If we talk about hydrogen, now hydrogen has only one electron. It has only one electron. So the first electron will be entering the 1s subshell. We'll write like this. The superscript word, here I am writing like this 1. This 1 which is written as the superscript basically indicates the number of electrons which are present in the element, right? Like in the case of helium, that there are 2 electrons, so it will be 1s2. Why we have written 1s2? Because S subshell can accommodate maximum of 2 electrons, right? In the case of hydrogen, since there is only 1 electron, so we had to write 1s1. Now in the case of lithium, the atomic number is 3, that means there are 3 electrons. So 1s will be 2, after 1s comes 2s, and it will occupy only 1 electron, because total electrons are 3. In the case of beryllium, atomic number is 4, so it will be 1s2 and 2s2, right? In the case of boron, atomic number is 5, so it will be 1s2, 2s2. Since boron has 5 electrons and 2s is completely filled, so after 2s comes 2p, and 1 electron space is left, so it will be 2p1. In the case of carbon, atomic number is 6, so it will be 1s2, 2s2, 2p2. We know the p subshell can accommodate maximum of 3 electrons, right? We have 6 electrons. We have just understood it. There are maximum of 6 electrons that can adjust in p subshell. So 2p will be filled up to the point where we will get 2p6, right? That means in the case of nitrogen, atomic number is 7, it will be 1s2, 2s2, 2p3. Oxygen, atomic number is 8, so 1s2, 2s2, 2p4. Then comes fluorine, atomic number 9, so it will be 1s2, 2s2, 2p5. Then comes neon, so it is atomic number 10, so it is 1s2, 2s2, 2p6. Now we know in periodic table the noble gases are very important to learn, right? We need to know which are the noble gases available. Since neon has the atomic number of 10, and in the case of neon you see the second shell is completely filled. We know second shell has 2 subshells, 2s and 2p, and here 2s and 2p are completely filled. 2s can have 2 electrons, 2p can have 6 electrons, and both subshells are completely filled, right? That is why neon has the noble gas configuration. It has the noble gas configuration. Now when we write the electronic configuration of sodium, here it has atomic number 11. There are 2 ways I can write it. Either I will write it in the similar way, in the proper way, from starting from 1s till end, I will write it like this. It will be 1s2, 2s2, 2p6, and then 3s1. One is this way to write it. Another way is that just before the sodium, which noble gas is appearing, right? So we'll use that noble gas as the reference. Since here neon is the noble gas and it is a reference, right? We'll take it as a reference that up to neon, 10 electrons are already filled. They are, and up to neon, all the subshells are completely filled. You can see it in the neon case also. After neon comes sodium, and it is in the case of sodium, 1 electron is extra, right, as compared to neon. Neon has 10 electrons, sodium has 11 electrons. And this 1 extra electron will be filled in 3s subshell. So it will be neon 3s1, like this. That means in the case of magnesium, it will be neon 3s2, right? Another thing is that up to neon, it is only second shell. Beyond neon, we are using the third shell, right? So it is totally a new shell where we are filling the electrons. In the case of aluminium, atomic number is 13, so it will be neon 3s2, 3p1. So similarly, up to silicon also, we can fill then phosphorus, sulfur, chlorine, argon, potassium, and calcium. Up to calcium we can fill, right? Here also if you see, argon is another noble gas. Argon is another noble gas, and in the case of argon, when you fill the electronic configuration, here it will be like this. 18 is atomic number, so it will be 1s2, 2s2, 2p6, 3s2, and 3p6. This is the configuration of argon, right? So here also in the case of argon, the third shell is completely filled, right? 3s2 and 3p6 are completely filled, right? In the case of argon. That means if we go to the potassium and I write the configuration of potassium, after 3p comes 4s. If you look at here, after 3p comes 4s, right? So we have to fill the 4s subshell now. So if we talk about the potassium, I will write its configuration like this: Ar 4s1. And then in the case of calcium, I will write Ar argon 4s2. After calcium comes scandium, and scandium has atomic number of 21. Scandium has atomic number of 21, and after 4s comes 3d subshell, right? If you look at here, after 4s we have the 3d subshell. That means now the electrons will be filled in the 3d subshell, and 3d subshell, d subshell can have maximum of 10 electrons because it has 5 orbitals, right? It has 5 orbitals. So I will write in the case of scandium, it will be Ar 4s2 3d1. Then titanium, it will be Ar argon 4s2 3d2. Vanadium, it will be 23 atomic number, so it will be argon 4s2 3d3. Then chromium is 24, so it is Ar. Now if you observe, in the case of chromium, I have just marked the asterisk. That means there is some exception in the case of electronic configuration of chromium, and that exception is, now after 3d3, what should come? After 3d3, we should have 3d4. But here in the case of chromium, we have Ar 4s1 3d5. Right? So there is a jump in the case of 3d3 to 3d5. And what is the meaning of this configuration? We will understand shortly. Right? Just have some patience. We will definitely understand. In the case of manganese, atomic number is 25. Now here also, it will be 4s2 3d5. It will be 4s2 3d5. Iron 26, it is argon. Now again, it is 4s2 3d6. Right? Up to nickel, it will be like this only. Nickel is 28, so it is argon 4s2 and 3d8. Now again in the case of copper also, you can see asterisk is put. That means there is some exception in the case of configuration of copper. Now it has atomic number 29, so its configuration will be Ar 4s1 3d10, right? Again it is 4s1 3d10, and there is some exception. And what is that exception? We will understand. In the case of zinc, it will be Ar 4s2 3d10. So up to zinc, if you see, zinc and copper are these two elements which have complete d subshell, right? Copper and zinc are two elements which are completely filled d subshell. So I hope you understood how do we fill the electronic configuration of these elements using the first two principles. The first principle is, as usual, it is Pauli's exclusion principle, which has explained to us that only two electrons are present in any subshell, any orbital, and any two electrons cannot have same set of all the four quantum numbers. Then second was Aufbau principle, that electrons are filled in the subshells in the increasing order of their n plus L value. And we have done it here. We have found the n plus L values and arranged them in the increasing order. Also, if two subshells have same value of n plus L, then the subshell having lower value of n, right, principal quantum number n, will be filled first because it will have lower energy. So accordingly, we have used these concepts and we have done the configuration up to the element of zinc. Now, a few important points regarding the rules which are studied till now. First important point is that subshells with the half-filled or fully filled electronic configuration are more stable as compared to other configurations. Right? This is very important rule. It's very important. The point is saying the subshells which are having half-filled or fully filled configuration are highly stable in nature. Right? That means in the case of P subshell, if I talk about half-filled, it will be like this. Right? All the electrons should be of same spin. All three electrons are having same spin. So this is half filled. This is half filled configuration. And if we talk about the fully filled, we know it, 3 electrons of one spin and 3 electrons of other spin, different spin, right? So this is fully filled. These two configurations are highly stable in nature. Now, why these configurations are highly stable? It is because of one important concept of exchange energy. One important concept is exchange energy, right? We will understand this concept in our upcoming video, right, where I will be utilizing it in one of the questions which I will solve. Right now, just understand that exchange energy is the reason that why half-filled and fully filled subshells are highly stable in nature. So in the case of P subshell, the half-filled is like this and fully filled is like this. Similarly, in the case of D subshell, the half-filled will have 5 electrons and all the electrons will be of same spin. And in D subshell fully filled, 5 electrons will be of one spin and remaining 5 electrons will be of opposite spin, like this. So this is how D subshell is again fully filled and half filled. Important thing is that if we compare the stability between half filled and fully filled, right? If we compare the stability between half filled and fully filled, in that case, the fully filled is more stable. The fully filled is more stable than half filled. If we compare their stability of these two. So cutting the slack, important thing is half filled and fully filled both are stable. But if we compare the stability among these two, then fully filled is more than half. Okay, fully filled is more than half. Now to apply this concept in one of the questions, one question is there that one electron is to be removed from both oxygen and nitrogen. So we have to remove one electron from both oxygen and nitrogen. In which element more energy is required? The question is asking in which case we have to give more energy to remove the electron. Now in the case of oxygen, if we write the configuration, it will be 1s2, 2s2, 2p4. That means the 2p4 will be like this. 1, 2, 3 and 4. And in the case of nitrogen, the configuration is 1s2, 2s2 and 2p3. So you see in that case the last most subshell is 2p3 and 2p3 is like this, right? So if I draw the 2p3 subshell configuration, it is half filled. It is half filled, right? And we know half filled configuration are highly stable as compared to the normal configuration. Now oxygen doesn't have either half filled or fully filled, but the nitrogen has half filled. That means the electronic configuration of nitrogen is more stable as compared to oxygen, right? This configuration, electronic configuration of nitrogen is more stable as compared to oxygen. So if nitrogen configuration is more stable, then definitely more energy will be required to remove electron out of it. Understood? So oxygen requires less energy, nitrogen requires more energy because nitrogen has half-filled configuration. Next point. Next point is exceptional configurations of copper and chromium, which we are discussing earlier. Now in the case of copper, if you understand this thing, copper has the configuration of Ar, argon, 4s1, 3d9. This is the configuration which we had written, right? Just a second. Just a second. Yes. Okay. So why do we get the exceptional configuration in the case of copper? Now if you look at the configurations above, from iron we had 4s to 3d6. So cobalt will be 4s to 3d7. Nickel will be 4s to 3d8. So if we follow this trend, the copper should be 4s to 3d10, right? Sorry, 4s to 3d9. If we follow the trend that in the case of these 10 elements, we are filling the D subshells, then from iron it is 3d6, cobalt 3d7, nickel 3d8 and copper should be 3d9. That means in the case of copper, the configuration should be 4s2 and 3d9. And if I draw it, what will happen? The 4s2 is like this. This is 4s2 and this is 3d9. This is, we have drawn the 3d9. Now if you look at here, in the case of 3d9, it requires only one electron to become fully filled subshell. And 4s2 is fully filled. This 4s2 is fully filled, and 3d9 is having no specific configuration. It is neither fully filled nor half filled. So what will happen? One electron from 4s will excite and jump into the final orbital, last orbital of 3d, right? And in this way, what will happen? The configuration of copper will change from 4s to 3d9 to 4s1, 3d10, like this. Now the configuration has changed to 4s1 and 3d10. In this configuration, if you see, the 4s is half filled and 3d is fully filled. And because 4s is half filled and 3d is fully filled, both are highly stable, right? Both have become highly stable as compared to the above configuration, where the 3d9 was neither half filled nor fully filled, so it was less stable. Therefore, copper attains the configuration of 4s1, 3d10, right? Similarly, in the case of chromium also, just like we have understood the chromium copper, the understanding of configuration of chromium is homework for you, right? Understand in a similar manner, because we write chromium. If you look at here, chromium comes after vanadium, and the vanadium is 4s to 3d3. So that means chromium should be 4s to 3d4. Chromium should be, it should be 4s2 and 3d4. This is what it should be, but actually it is what? Actually it is 4s1 3d5. This is the correct configuration. Why it is so? In the similar way, right? Try to do it, you will understand it properly and solve it in your own way. I have explained you in the case of copper. In the similar fashion, chromium can also be done. Now important point is that this n plus L rule, which we have applied in the case of Aufbau principle, is applied only to the multi-electron species. This is very important understanding of the Aufbau principle, right? It is applied only to multi-electronic species. That means the elements or the species which has more than one electron. So in another sense, N plus L rule is not applicable for hydrogenic species. What are hydrogenic species? We can say they are hydrogen-like species. Like we have He plus, right? Li2 plus or beryllium 3 plus. For these kind of species, this rule is not applicable. Why? Because for hydrogenic species, all the subshells, for these hydrogenic species, all the subshells of a particular shell are of same energy. That means if I talk about the third shell has 3s, 3p and 3d, right? Third shell has 3s, 3p and 3d. If this species is multi-electronic, then we can say if the species is having more than one electron, in that case, N plus L rule is followed, and we have already applied the rule, and we know in that case the configuration will be, the energy order will be 3s will be less, then 3p, then 3d. This is the order, right? In case of multi-electron species. But if I talk about hydrogen-like species, that is hydrogenic, in that case, if we talk about 3s, 3p and 3d, these three subshells are present in third shell, they will have same energy. They will have same energy, right? This is the meaning of this statement. Similarly, in the case of second shell, 2s will have same energy as compared to 2p. Both will have same energy, right? This is the meaning of this point, that N plus L rule is not valid for hydrogenic species, and all the subshells will have same energy which are present in a particular shell. In case of hydrogenic species. Next very important rule is Hund's rule. Now Hund's rule says that the pairing of electrons in a subshell, pairing of electrons in an orbital of a subshell is done only after the subshell is half filled with electrons of same spin. Now what is the meaning of this thing? To understand this thing, let's try to write the electronic configuration of three elements: carbon, nitrogen and oxygen. Now carbon is 1s2, 2s2 and 2p2, right? 1s2 is fully filled, 2s2 is also fully filled, remaining is 2p2, right? That means 2p subshell has 2 electrons. So when we write the 2p2, this is how we do it. Second 2p subshell has, this is 2p subshell, 2p subshell has 2 electrons. Important thing is when you write the configuration of carbon here, both the electrons should be filled in different orbitals. Both the electrons should not be filled in same orbital, right? Why? Because Hund's rule says if you fill both the electrons in same orbital, what will happen? We will get this thing. If you fill the same both electrons in same orbital, it will be like this, right? 2p will be like this, and it is not correct way because it violates the Hund's rule. It is against the Hund's rule. Hund's rule says that pairing of electron, this is pairing of electron, right? This is the pairing of electron. And Hund's rule says that it is done only after all the orbitals in a subshell are half filled with the electrons of same spin. That means 2p can have, or we can say p subshell can have 6 electrons. So before pairing is done, it must have 3 electrons of same spin. In that sense, it will be half filled. That means if I write the nitrogen configuration, it will be 1s2, 2s2, 2p3. And here this 2p3 will be written like this. 3 electrons are there, so now it is made half filled. Once half filling is done with the same spin of electrons, pairing will start. In the case of oxygen, we have 1s2, 2s2 and 2p4. Since 2p has 4 electrons, how do we fill it? First, make it half filled, then do the pairing. Now we do the pairing, right? So pairing is done only after all the orbitals are half filled in a particular subshell. This is the meaning of Hund's rule. Another example is iron. Now iron has the configuration how much? It has 26 atomic number. So when we write the 26 atomic number, it will be 1s2, 2s2, 2p6, 3s2, 3p6 and 4s2, 3d6. Now 3d subshell is not completely filled. We know d subshell can have 10 electrons, but here we have only 6 electrons, right? So if we have 6 electrons, how do we fill them? Again, by following the Hund's rule principle, d subshell can have 5 orbitals, so all the orbitals are first filled with single electron of same spin. Now it is half filled. We have 1 electron left, so we do the pairing now. Now one of the d orbital is paired. This is how we do the configuration by using the Hund's rule. Understood? So by understanding these 3 laws, which are very important, you can easily solve this question. This question is for you only. Try to solve this problem and answer me the correct option of this question in the comments so that I can get to know that you are actually understanding the concept properly. So solve this problem so that we can have the proper understanding of your idea, that you have understood the concepts. Last few important formulas which are very important to apply in these rules are: first principle is, first rule, number of subshells in a shell. In any shell, the number of subshells which are present is equal to the value of n. Is equal to the value of n. How? If I talk about first subshell, right? First shell. Let's say I write here shell. If I talk about first shell has only one subshell, right? because number of subshells, how many subshells are there? Based upon value of n. So first shell has the value of 1, so it has only one subshell, which is S subshell. Second shell has value 2, so it will have two subshells, right? So these two subshells are what? These two subshells are S and P. Similarly, if we talk about third shell will have three subshells, so it will be 3S, 3P and 3D, like this. So number of subshells in a shell is equal to value of n. Next rule is number of orbitals in a subshell. So in any subshell, the total number of orbitals which are present are 2l plus 1, right? It is 2l plus 1. Now if we talk about S subshell has value of L equal to 0. That means how many orbitals are there? If you put L is equal to 0 in this equation, it will be 1 only. And if I talk about F subshell has L value as 3, right? So if the value of L is 3, so it will be 2 into 3, 6, 6 plus 1, 7. There are 7 orbitals, right, in F subshell. There are 7 orbitals in F subshell. So the formula is 2L plus 1. Next is number of electrons in a subshell. Now simple point is there, if we know the number of orbitals in a subshell, so doubling that value will give the number of electrons, because each orbital contains 2 electrons. So if the F subshell has 7 orbitals, that means total number of electrons present in F subshell is 14, right? So the number of electrons formula is twice of 2L plus 1. It will be twice of 2L plus 1. So both these formulas are in the terms of angular momentum quantum number, right? Next formula is in the terms of value of n. Now it is saying the number of orbitals in a shell. So number of orbitals in any shell is equal to n square. It will be n square. Remember this thing. That means third shell, if we talk about third shell, it has 9 orbitals. And how is it possible? We know third shell has 3s, 3p and 3d. 3s has only one subshell, 3p has 3 subshells and orbitals. 3s has 1 orbital, 3p has 3 orbitals and 3d has 5 orbitals. So 5 plus 3 plus 1, it is 9, which is also 3 square, right? So number of orbitals in any shell is n square. So number of electrons will be twice. So number of electrons are 2n square. In any shell, the number of electrons are 2n square, right? So these are the important formulas. Last but not the least, few more things are there. That value of L can never exceed the value of n in any shell. For any shell number, the subshells which are present in that shell will never have the value of L greater than n. Because we know the value of L, it ranges from 0 to n minus 1. This is the range of value of L. So if we talk about the third shell, here the value of n is what? 3. That means in third shell, we will have the subshells which will have value L is equal to 0, 1 and 2, right? So the value of L will never be greater than the value of n. So 3 is for S, 1 is for P and 2 is for D, like this. Similarly, last point, that the value of M doesn't exceed the value of L. Now what is the meaning of this point? That means that if we have the value of L equal to 3, right, L equal to 3, the value of M will always be less than equal to L, greater than equal to minus L. That means in this case, the value of M will be less than equal to 3 and always greater than equal to minus 3. This is a range of value of M. That means here if L is equal to 3, M can never be equal to 4. The value of M can never be equal to 4 or greater than 3, right? So these last two points are there which are very important in solving the problems. So by using these points only, the bottom given question is for you to solve it The question says which of the following set of quantum numbers represents an impossible arrangement. So you have to tell that which of these values are given and which of these arrangements are not possible for the proper address of electron. Right? So by understanding this question and by solving this question by you only, definitely, we will conclude this lecture, we will conclude this video. So what we have learned in this video, we have learned the important formulas which are important for the finding of subshells, electrons and orbitals in any shell. And we have understood three important rules. One is Hund's rule. Then we have the Pauli's principle. In Pauli's principle, we have understood the electronic configurations and exceptions, and how half-filled and fully filled are very important to learn. And we have to go through the exchange energy. That we'll do later on. Similarly, we have gone through the first principle, that is Pauli's exclusion principle. So I hope you understood the lecture properly, and I hope you have done your notes completely also. Stay tuned for the next lecture, because in the next lecture we will understand about the probability distribution curves, or we can say xi and its significance of xi, which we have to understand because it is very important from the perspective of Schrodinger wave equation and wave nature of electron. So stay tuned for the next video. Thank you. Take care. Goodbye.